Behold, the strength of steel and ambition, bridging dreams into reality. We are the Steel Center Bridge team from the University of Alberta, and today we're excited to share with you our journey in designing and fabricating a state-of-the-art steel bridge. Our team is composed of dedicated students divided into specialized groups. The design team, who engineered our bridge from concept to blueprint, the marketing team, who effectively communicated our vision, and the finance team, who managed our resources to make this project possible. Join us as we dive into this creative process behind our design and showcase the transition from paper to structure. Let's get started.
At the very beginning, our design team had two conceptual plans for the bridge geometry, going with a truss bridge or an arch. Considering the modern look of the arch, the innovation it has, and of course the challenge of designing it, we decided to go with the arch. But simultaneously, we wanted to use the benefits the truss would give to our bridge. So we started with this model. After going deeper into the model, we found out that since we have height restrictions and no fixed supports, and since we couldn't have a flush deck for the loading, we started to modify the model. Although it was against our will, we removed the upper part of the arch to see if we could go with the Warren truss by itself. But since we reduced the height of the deck midspan, we saw a great reduction in the moment of inertia, which leads to larger deflections. To make up for this reduction, we needed to increase the section's area, which would increase the weight of the structure as well. So it wasn't desirable and led us to modify it again. So finally, we came up with this geometry. It's a combination of Warren truss and reverse arch that give us sufficient vertical stiffness, which reduce the vertical deflections and at the same time will give us a lighter bridge. I believe I can consider this finalized model as the most efficient and qualified one in addition to its aesthetics and innovation. So we tried our best to minimize the number of connections in the bridge and have the majority of them prefabricated in order to reduce both fabrication time and costs. To begin with, we simplified the design by concentrating all the upper connections of the bridge column at a single splice along the column's length. These concentrated maybe 4 or even 5 connections in one. We can see different connection types for our bridge. For example, in the Warren truss, we needed a moment connection and a clear path for the load. So we came up with this male-female connection, which is a plate welded in one side and bolted in the other. It transfers moment and it's easy to assemble. For the arch, we wanted to have simple hinge connections that lead us to this connection. Although in the plane of the arch, it's a hinge, it will slightly increase the out-of-plane stiffness, which helps the out-of-plane stability of the arch. We can see that we did our best to create a hinge behavior in all the arch connection by using simple truss connections with gusset plates. For instance, in this connection, we aligned our member and designed the connections in a way that the center lines of all members intersect in one point with the least amount of eccentricity. The gusset plate is welded to one member to reduce the assembly time, and also it is used to fix the alignment of the other members. So, to wrap it up, this is our finalized bridge model. A simple though beautiful bridge, a combination of different structural systems using both moment and hinge connections, and I can say a structure that respects the historic ambience of Quebec City and its traditional architecture.
To analyze our bridge, we modeled it in SAP 2000. Our main goal was to optimize the bridge to have a lightweight but a high stiffness at the same time. We designed it considering tension-only members for the braces, lateral torsional buckling of the main deck, simulating the friction between the base plates and the ground as a spring, and so on. At the end, for the design check, we first defined an envelope considering different loading scenarios and an amplification factor to consider the weight of the bolts and welds. And finally, we checked internal forces and deflections to see if they fulfilled our criteria.
To go from design to fabrication, we faced a few challenges that were great learning opportunities for us young engineers. One of the challenges that we faced was that we designed our model with assumptions such as the section sizes and envisioned our shapes to be fabricated a certain way. But when it was time to bring the design to reality, we had to make some on-the-fly adjustments to make sure all of our parts fit together and the fabrication strategy would work. I would also like to give a huge shout out to our sponsors, CISC, Collins Steel, Neat Group, the Steel Center, Computers and Structures Incorporated, and Associated Engineering. We couldn't have done this without you.